I'm Doug, Stand-Up Physicist. Today I'm going to talk about light, art, and physics. Light plays a central role in both art and physics. Right here I've got my key light, my fill light, and I've got a backlight. Painters have always been very concerned with light. I particularly like the work done by Impressionists, trying to explore how we take in light information. They played lots of very interesting games, from the pointillists who made dots of everything, to people who realized that the brain is better and more accurate at processing lines than where colors are. And so they would actually be really sloppy with the colors and really precise with the lines, because they understood that's how we think about light. Physicists have also done a lot of work with light. In fact, all the most important physicists made some kind of contribution to our understanding of how light works. Well, why is there this correlation? Think about the difference between light and darkness. When it's dark, we go to sleep, unless we're out partying. And plants, they forget about it. When winter comes, it gets really cold. Plants just go into major hibernation. If it was dark all the time, the world would be dead. So light clearly is really important. It's important on numerical grounds alone. If you go out and you count the number of particles that make up light in the overall universe, and you compare that to the number of particles that make up you and I, stuff with mass, you'll find out that light particles outnumber massive particles by 10 billion to 1. So the universe, to first order, is only about light. Fortunately, there's a little mass for you and me to have interesting lives, but really, it's mostly about light. I started to think about light when I got really stuck. I had been working in the early 90s on this little math widget that explained one experiment, and I was really proud of that little widget. I showed it to a professor at MIT, and he said, well, it's interesting, but not very interesting, because it only explains one result. So a year later, I came back and I said, now my widget can explain 3 things. And on his way back from the Chinese food truck, he said, that's just a widget. That's not a theory. You need a theory for why your widget even exists. Well, I agreed with him and went on my way. I just needed to come up with a theory. Now, a theory is a structure that allows you to calculate a whole bunch of things. And each and every one of those calculations has to be consistent with current tests of the world. And if you do some more sensitive tests, it should be even more accurate than our current theory. This was quite a ridiculous thing to look for. So instead of going straight at the target, I veered off, as is my way, and decided to think about light, but from a visual perspective, using the visual part of my brain, not worrying about equations, because light has some odd properties. For example, nothing can go faster than the speed of light in a vacuum. And you think, well, if you try a little harder, shouldn't it work? The answer is no. You cannot go faster than the speed of light. And so you wonder, well, why? That's what I thought about. Light comes in clumps, and light comes as a wave. But a clump is not a wave. A clump is very precise, very much centered in one spot, and a wave is extended over a distance. So how can it be both? Well, I wondered about that. And in tonight's program, I'm going to show you two works of art that I made that deal with these two issues. But first, I have to give you an art history lesson. Rene Magritte was a French surrealist who liked to wear bowler hats. Surrealists knew how to paint very realistically, but they would compose images which had all these realistic components that somehow didn't make any sense whatsoever. Or they challenged assumptions that we long held about what things really mean. Magritte's most famous painting is "This Is Not a Pipe," because it certainly looks like a pipe, but it really is a painting of a pipe. And it's a painting of a description of "this is not a pipe," but is the whole thing just a painting? Or what do the words mean? What do the representation of the pipe mean? Well, it can get kind of confusing. It's fun to think about. I really liked his painting of the guy staring very intently at an egg and painting a bird. This painting stumped me for a while. I said, this is Magritte. There must be a riddle. There's this street and there's this sky. And I realized that's a nighttime street and a daytime sky. Very good stuff. So, inspired by his work, I created The Speed of Light according to Rene Magritte. It reads along the top, "The speed of light, c, is not a velocity." I got a French physicist to actually make sure that all my accents were pointed in the right way. It's the kind of detail I was never able to master. So the idea here is that we are all familiar with speed. And one of our experiences with speed is if we try a little harder, we can go a little faster. Well, that doesn't work with light. Doesn't matter how much harder you try, you will not go any faster. The speed of light, c, is what's called an invariant. Frequency and wavelength, those are not invariants. If you try a little harder, well, then you will get a speed that is the same, but the frequency will go up and the wavelength will go up in such a way that the speed stays the same. You have to think about this speed limit, that absolutely nothing can go faster than light in a vacuum, in a way that's different than you think about velocity. In the bottom it reads, again in French, "There is no space without time, no time without space." The fundamental commodity in nature, in my opinion, is an event in space-time. So you must always have time with space and space with time. And then the speed of light, c, has to do with the relationship between time and space. So if we go over to the left-hand side of this bas-relief, I guess we call it, it says time eclipses space. The idea there is that if you have a very, very low relative velocity with some other object, then you can sit around and tell lots of stories. You've got the time to do it. So, for example, I could tell you that I was born in Bronxville, New York, and I was raised there by my parents, and I could keep on going because you and I have a low relative velocity to each other. There's a lot of time for us to share history. If we go over to the next panel, well, we have a higher relative velocity between the observer and the observee. So there are a few chances to tell stories. But it's not an infinite kind of situation. There are only like 8 or 9 chances to tell a story, and they're gone. In the third panel, well, there's a couple chances to tell a story, and that is it. So it's like somebody just cruising on by, you wave at them, and they might say, whoa, and that's it. And then in the final panel, we have what I consider to be the key message about the speed of light. That for the speed of light, time is space. There is only one chance to communicate one little bit of information. Now, if you miss that chance, well, that's it. One of the neat things about this idea is that it helps me with an issue that comes up in cosmology. In cosmology, we learn that there are all these galaxies that are receding away from us at very high relativistic speeds. Why do they not like us so? Why are they speeding away at these tremendous velocities? And the idea is that we share very little history with them. Sure, we were there together in the Big Bang, but we are not together anymore. We only share a slight history together, and that's reflected in our high relativistic velocities to each other. We can't tell them big long stories. They've got things to do in another part of our universe. So when I hear that something has a high relative velocity to me, I know we don't share much in common. For material with really low relativistic velocity to you and I, say the Earth around us, this indicates that we've shared a huge amount of history. And what we know is we've all been on this planet for 4 billion years, which in my book is a long time. The relativistic velocities indicate that shared time together. So why can nothing go faster than light? Well, this piece helps me deal with that because it says it's not about velocity, it's about time's relationship to space. And when that is the simplest relationship there is, that time is space, that is what things with no mass that travel at the speed of velocity, that's their relationship. And it doesn't matter how or who looks at it, time will be space. Now the frequency can change. The wavelength can change. For example, those coils can be tighter or they can be looser. But if time is space, then there's only one kind of chunk of history one can deal with. This next piece has a long title. Groups of coherent photons behave like waves and particles. The goal here is to try and understand the title. Groups of coherent photons behave like waves and particles. It's an odd notion that light can be both at a point and yet have properties extended through space. Our experience tells us that it really does have these two properties. Light does come in clumps if you have a digital camera, because on that digital camera you have a CCD chip, and that literally counts the number of photons, and based on that it creates an image. But we know that light comes as an extended wave with slight variations. You've seen a rainbow which shows a gentle change of wavelengths. We need to focus, though, on words that matter. I remember in particular an article in Scientific American that did a bad job of this. They focused on the two-slit experiment. That is an experiment where you take some light that is coherent and you shine it on two slits, and it appears to kind of go through both in a way that ends up giving you an interference pattern. If you decrease the frequency of light showing up on these slits such that a photon would only show up once a month, you still see an interference pattern. And that seems very odd, because how could the photon interfere with something else? It somehow has to interfere with itself. There are entire books written on this subject, and some scientists spend their careers trying to come up with even more sensitive ways to show that light is a wave and a particle. Or to catch it just being a wave, or just being a particle, but that never happens. One error is that the number of slits doesn't matter at all. If you go from the two-slit experiment, which shows you quantum interference, you can go down to one slit and you can still see that light is a wave. The reason is because you get what's called quantum diffraction. And that's every bit as wave-like as quantum interference. So the number of slits completely and utterly does not matter. In the opening image that accompanied the article, they featured Einstein arguing with Niels Bohr. Bohr was the fellow who did a lot of important work in quantum mechanics. And Einstein just didn't get the logic of these two. He understood the math, but he was bothered by it to such an extent that he kept trying to find ways to fool Bohr, and it never really worked. The thing that bothered me, though, was they showed Einstein and Bohr holding a flashlight. And this was the one time that I wrote the editors of Scientific American to complain, because a flashlight is an incoherent light source, and coherence of the light source matters. If your light source is a flashlight, that is incoherent, and it would show nothing of interest in any of these two-slit experiments. So what is incoherent light? I try to represent incoherent light with that turquoise panel in the middle. Each and every one of those squares is supposed to represent a volume in space-time with a certain number of photons in it. So each square is, say, a centimeter long, a centimeter wide, a centimeter deep, by a nanosecond long in time. And depending on the color, it's either got 0 photons or as many as 7 photons. And the gradations in between the white and the darkest turquoise has 1, 2, 3, 4, 5, and 6 photons in each little temporary box. I tried to make this totally random by rolling a dice for each and every one of those squares. And depending on what I got rolling that dice, that determined what that square was. Now, it made it take a long time to color all of those, but I can tell you that that is truly a random pattern. If you take that type of source and put it in a two-slit experiment, you will not see wave phenomena. The panel on the left and the right, those are coherent sources. The one on the left is supposed to be coherent in time. If you come back at a later time, you'll find a row that's got 7 photons. Come back a little later, 0 photons. Then come back a little later, 3 photons. Where you are in time determines how many photons you see. And there's a definite pattern repeating in time. The image on the right is supposed to represent photons organized in space. If you go to this particular place, you will find no photons. Over there, 2 photons. And over there are 5. And you keep on going to a different spot, you continually get a different type of information. So I can see a wave-like pattern. Only the light that is coherent in time or coherent in space can behave like a wave and a particle. If you were to focus in on any one box, you would not be able to tell whether it came from the coherent source or the incoherent source. Because if you just look at one box of space-time, that's not enough information to figure out whether it's coherent or it's incoherent. What you must do is you must look at a group of those boxes. You must look over an area of that image. And when you look over an area of that image, it's clear that it has a wave-like property if it's coherent, because it follows this pattern: high down to low, up to high, down to low. And yet each one of those boxes has in it concrete numbers of photons in clumps. So this image helps me understand why groups, an area of that picture, of coherent, the left or right images, photons, behave like particles because there are photons in each one of those boxes, and waves because I can see the wave-like pattern. In this show, I didn't feature any equations. Well, there is math behind both of these riddles. For the speed of light, it's called the Lorentz transformation. And for the particle wave nature of things, it's called the wave function. But these visualizations help me understand the why. Why do I have to use this odd math to describe the way that light works? Thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star.
I like to do both science and art. What does it take to do science and art? Well, the key is in the eye. Now take a real close look. See how big my iris is? It's like, it takes a lot of practice to get it that big, you know? And once it's that big, you can suck up information so much faster. Whether you're doing physics or you're doing art. That sounds like a bunch of doggy crap. I think that boy was doing some serious drugs. Now I know, because, well, I've done some serious drugs myself. Like one time, I was hanging out with my junkie friends, and they told me, they said, you shouldn't do a week's worth of drugs in one day. But I made a little mistake. And I got the biggest irises. Oh my gosh. But here's something weird that I figured out. That you can get in a weird state of mind without doing drugs. Can you believe a guy like me can get in a weird state of mind? It's true. It's so true. You don't need drugs. You just let your mind go free. I bet you just went